Today we're delighted to have David Vogan speaking about what's special about special.
Thank you. It's certainly wonderful to be back here. I have an enormous amount of experience sitting in the back rows of these classrooms, and I understand the attitudes and the conversations that take place back there, so don't think it's a secret. It's difficult to be on this end because of what amazing people were on this end when I was sitting in the back. I can't live up to their example, but I'll be talking about mathematics that I learned here, and so at least it's interesting mathematics. So I have to explain what all the words are, and let's see. No. I'm not sure this is going to work at all. I think the little clicker. Let's see. I think the little clicker doesn't work. Let me just try unplugging it and plugging it in. And that doesn't. Effect.
Would you like to try an alternate clicker?
I think it doesn't matter. I can do fine with the keyboard. So this isn't so helpful. So what I'm interested in, what I learned from Paul Sally to be interested in, was infinite dimensional representations of real reductive groups. And those things are very complicated. And in mathematics, when you have something complicated, what you try to do is attach to it something simpler that reflects interesting properties. So I'm going to talk about a simpler invariant that's attached to an infinite dimensional representation by the credit in this talk is, I learned a lot of good things here, but from George Lusztig, what I learned was how easy it is to get people pissed about credit. And I think most of the people that I will get pissed about credit are not here, so it's okay, sort of. But anyway, I want to talk about ideas which are related to work of Janssen and Zuckerman about attaching a simpler invariant. So what this simpler invariant is, it's two things: a finite dimensional representation of a Weyl group and a vector in that representation. Using this vector, you can construct a Weyl group subquotient representation called sigma of pi, and Tony Joseph showed that this Weyl group representation has a natural irreducible quotient that I'll call sigma j of pi. I used to give Lusztig credit for this quotient, but I did that in front of Tony Joseph once. And anyway, so these things, the Weyl group representation and the vector in it are integer things. And one of the many things I learned here is that things defined over integers are good things. Sorry, David. So this is the picture. I want to attach to an infinite dimensional representation a representation of a finite Weyl group. So before I tell you how to do that, I'll say that in the case of GLN, the Weyl group is the symmetric group, Sn, and this representation sigma of pi and Joseph's quotient of it are the same. It's an irreducible representation, and any of the symmetric group representations can appear. So that's nice. But for groups other than GLN, only certain Weyl group representations can appear. And Lusztig understood how to describe these representations, and he called them special. And his 1979 definition of special was part of his analysis of the irreducible representations of finite Chevalley groups. So what I'm going to do is tell you roughly how you define this Weyl group representation, sigma of pi. I'm going to tell you some integrality properties of this representation. And I'm going to show you how integrality properties force Lusztig's special representations on you. So that's a very vague version of what I'm doing. That even corresponds to the three main chapters. We'll see if that actually works out. So the first thing I have to do is tell you how to define a Weyl group representation. So remind you about the Weyl character formula, that if K is a compact connected Lie group and T is a maximal torus, pi is an irreducible representation, then the character of pi is this smooth function where you take the trace of the operators pi of k, you get a smooth function on k, which is conjugation invariant. And so since every conjugacy class in K meets this maximal torus, to understand this character, it's enough to understand it on the maximal torus. And what Hermann Weyl showed is essentially, I mean, there are going to be a lot of little lies, so I think this might be the first little lie. There's a dominant regular character gamma of T, so that the character takes this form. There's a numerator, which is the sum over the Weyl group of the sign character of the Weyl group times the W orbit of gamma. And then there's a denominator, which is what it is. So, which in particular, this denominator doesn't depend on pi. All the dependence on pi is in the numerator. So in the case of a finite dimensional representation of a compact group, this Weyl group representation that I want to attach is just the sign character of the Weyl group. And you see what's going on, that the sign character is telling you what the character formula is. Okay, so what happens if the group isn't compact anymore? So Harishchandra said that you could extend Weyl's character formula to real reductive groups, non-compact real reductive groups. In such groups, there's also a notion of a maximal torus. And if you have an irreducible representation of a real reductive group, then you can do something like taking the trace of the operators pi of g. Those operators are not trace class, so there's some regularization problem to define that trace, but the trace is a generalized function on the group, and in particular on regular elements of the group, it's an honest function. And Harishchandra proved that on a maximal torus, this function looks like this. You have the same kind of Weyl denominator, and now you have a sum of characters of the cartan, of the maximal torus, characters whose differentials are in a single orbit of the Weyl group. And so you have some finite integer combination. Well, yes, these coefficients are integers, and you have some finite integer combination of characters. So Harishchandra got this formula by looking at differential equations that are satisfied by the character and figuring out how to solve them. That basically, in very cleverly chosen coordinates, the differential equations came out to be constant coefficient differential equations, and so the solutions were exponentials. So what Harishchandra proved is that a character formula for an irreducible representation, it's a sum over characters whose differentials lie in a single Weyl group orbit. So more or less, this Weyl group representation that I want to define is related to the function that sends a Weyl group element to this coefficient AW. The first problem with that is that it isn't just a function of AW, that this have all these terms with a given differential. So that's one difficulty. Let's see on the next slide. So here's what the character of pi looks like, and what I want to do is make the Weyl group act on this character, and the way I want the action to work is I want to pretend that this character formula here is a function of gamma, function of this thing that's called the infinitesimal character. So the way you make a group act on functions is you put an inverse on the argument. So what would be sensible if this theta pi were really a function of gamma would be to apply a Weyl group element to it. You should replace, all these terms phi with differential W gamma, you should replace by phi primes with differential Wx inverse gamma. So to make that precise, you need to have a way to go from this character phi, which has differential W gamma, to a different character phi prime with this differential. And it's kind of clear how you should do that. You should take this character and you should act on it by this Weyl group element. The difficulty is that this complex Weyl group doesn't preserve the real maximal torus. And so you can't act by the complex Weyl group on characters of this cartan. So what do you do? So what happens, the place where the complex Weyl group wants to act is on rational characters of the torus. So there's a nice formula. If you have a root for the group in H star, and there's a co-root alpha check, the way the simple reflection S alpha acts on a rational character is you take the character and you subtract a multiple of alpha. For the character to be rational means that its differential on this co-root is an integer. So the action is just translating the character by a multiple of a root. So that's fine for rational characters, but our gamma isn't a rational character. So these, if we evaluate the gamma on these co-roots, we don't get an integer. So this is really the heart of the problem. And so you say, okay, we need it to be an integer. So you define the integral Weyl group to be the Weyl group elements which move gamma by an integer combination of roots. Yes?
Why can't we use this formula for a non-rational character?
Sorry, this...
The same reflection, the formula for the reflection.
Because this tau of alpha check would not necessarily be an integer, and, you know, alpha, we want a character of the group H. And this makes a perfectly good formula for the differential of a character. This is an element of H. This formula as an element of H star makes good sense. But it doesn't define, this non-integer multiple of alpha is no longer a character of the group H. That's the nature of the problem. So, as I say, we just look at the Weyl group elements for which this is true. And now everything works. If we have something in the integral Weyl group, this proposed formula magically makes sense. If we can define the phi prime that has to show up here in this way. I don't want to spend too much time on this, but if x is in the integral Weyl group, this x gamma minus gamma is the sum of roots. The Weyl group carries roots to roots, so this is also a sum of roots, and therefore perfectly good rational character of H. And what Janssen and Zuckerman proved that, well, this, as I say, this is one of the places where I'm not sure how exactly to talk about credit. These ideas certainly appeared in the work of Bernstein, Gelfand, and Gelfand before Janssen and Zuckerman, and I'm not sure what one should say. I think perhaps this theorem that I wrote is maybe first written down by Wilfried Schmidt, whose name I also didn't put, so maybe that's a reasonable balance. Anyway, that's the story. This formula, which now makes sense, is not only something that formally makes sense, it's interesting. It's an integer combination of characters of other irreducible representations. So that's good. So what? Okay, so here's where we are. I have this dominant regular weight in the dual of a Cartan subalgebra, a maximal torus, and the corresponding integral Weyl group. It makes sense to talk about the set of irreducible representations of G whose infinitesimal character is given by this gamma. And Harishchandra proved that that's a finite set. And so it's very natural to look at all the integer combinations of such representations. That's a finite ranked lattice. And what the theorem of Janssen and Zuckerman that I just mentioned says that the integral Weyl group acts on that finite ranked lattice. So these coefficients, these integers, m of pi prime pi, they make a matrix depending on x, and those integer matrices make a representation of this integral Weyl group. So it's not just defined over Z, that there's a really preferred basis over Z. So understanding that integer representation is a huge part of the problem of understanding characters of irreducible representations of G. So that's what we're trying to do.
Professor?
Yes.
I thought maybe I just missed what was happening earlier, but I thought the earlier character formulas gave us like theta pi in terms of characters of like the maximal torus.
Yes, that's correct.
Here it looks like pi primes and pi's are all in G hat.
That's right. So that this formula takes this theta pi is a generalized function on G. And the formula that's written here defines a new generalized function on G. And the theorem that's written here is that new generalized function is an integer combination of characters of irreducible representations. You're absolutely right. These integers here have nothing to do with the integer, okay. It's a very remote connection to the integers up here.
Okay, but like the theta pi of h, this is like applies to any h in G.
That's right. That's right. So this formula. I mean, there are a lot of details, a lot of i's to dot and t's to cross, but this formula tells you how to take this function defined on all of G and make a new function defined on all of G. And the hard theorem is that new function is again a finite integer combination of characters.
Your formula above, there's only H, compact H, right? In the below
No,
formula.
this was for any maximal torus, not necessarily compact.
Oh, H not necessarily compact.
Yeah. So there are a lot of things that I lied about. So this formula is only true on some Weyl chamber inside H. So, I mean, it's not really, the formula makes sense on all of H, but it isn't true. There's a wonderful picture that I learned from Paul Sally that if you have SL2R, then it has this this torus, and if pi is a discrete series representation, so here's R cross. There's 0. The character, if you write the numerator of the character, then it has this beautiful exponential decay, and it has this beautiful exponential decay on both sides. And that prevents it from being an analytic function there. You have this, well, it's e to the minus. So if this is x, then I guess probably this is x to the really? Yeah, I think it really. I may have this wrong, but in any case, the formula changes here, but Okay. All right. So, yeah. So I said that we got a representation, an integer representation of this Weyl group on the span of the irreducible representations of G with a certain infinitesimal character. Okay. So once you've got that, there's some natural stuff to do. So I said that if you act by the Weyl group on an irreducible character, you get an integer combination of other irreducible characters. And of course, it seems interesting to ask, what other irreducible characters do you get in that way by acting by this Weyl group? And so more or less this definition comes from Kazan and Lusztig, but it lives in many, many places. I'll say that pi prime is less than or equal to pi if you can find some Weyl group element that moves, that when you move your character pi, you get an integer combination of other characters, that this pi prime shows up. So what's equivalent to that is that there's an algebraic representation of the adjoint group, so that this pi prime is a subquotient of pi tensored with this finite dimensional. So this this notation is a little misleading. It's not a partial order because there can be loops, but this makes a directed graph structure on the finite set phi hat gamma. And once you've got a directed graph structure, there's probably better notation, but I'm going to call the left cone of pi. This is everything you can get to using this Weyl group. And inside that are the things where you can get there, but you can't get back. That pi prime is below pi, but it isn't true that pi is below pi prime. So it's very easy to see that this thing is, well, that both of these things span W of gamma invariant sublattices. And in particular, there's an equivalence relation. If you have these comparisons, if you can get from each one of these representations to the other by some Weyl group element, the equivalence classes are called left cells. And what the cell is, it's the cone where you throw out all the things where you can't get back. And since these are W of gamma representations, you get a W of gamma representation on the quotient, and that's called the left cell representation of W of gamma. And that's a free Z module, and the basis is this cell of equivalent representations. So this is definitely the world of representations defined over Z. Okay, so I'm gonna, I hope, make an example which might or might not be illuminating. The example comes in a couple of slides. I'm trying to decide if it would be better to skip to the example. I almost think it might be, and I'll come back to this. Oh, it's several slides. Okay, anyway, Here's the group U21, which is an 8-dimensional group of linear transformations of C3 that preserve the Hermitian form. And these preserve the metric. I don't know. Preserve that metric. So that's a non-compact group. It's a real form of GL3. The Weyl group is S3, so that's generated by two simple reflections, the transposition of 1 and 2 and the transposition of 2 and 3. It turns out that there are 6 representations of U21 having this infinitesimal character, and it doesn't matter if you know anything about what they are. That there's what's called a generic discrete series representation. There's a holomorphic discrete series representation, and where there's a holomorphic representation, there has to be an anti-holomorphic one. There's a representation that's called an AQ for some reason, holomorphic or anti-holomorphic. And I forgot to mention up here the trivial representation. So here's how the action of these simple reflections looks in this basis of 6 irreducible representations. If I take this generic discrete series representation and I act by the first simple reflection, I get the generic discrete series plus this thing that's called an anti-holomorphic AQ. If I act by the other simple reflection, I get, again, the generic discrete series and the holomorphic AQ. And so on. I mean, these are the formulas for how these simple reflections act in this basis. It's not enormously complicated, but it's somewhat complicated. The one thing I'll mention is the trivial representation. This is sort of like the representation of a compact group. I said that for a representation of a compact group, this Weyl group representation was the sign character. And here what happens is that the trivial representation, the action of the Weyl group is by the sign character of W. The simple reflections act by -1 on the finite dimensional. Okay, so that's, and I think I put an exercise in here. You can write similar formulas for how the Weyl group acts on principal series representations. Similar but simpler, and the fact that they're simpler is the reason that the principal series representations are not irreducible. If the principal series were irreducible, the formulas for how you act on them would be the same as these formulas for irreducibles. Okay, let me go back to tau invariance. Okay. So, in order to understand this Weyl group representation, I want to understand how the simple reflections act. And simple reflection is a group element of order 2, so the eigenvalues are +1 and -1. And it turns out to be interesting to single out the -1 eigenspace. So if I have a group representation, its tau invariant consists of all those simple reflections which act by -1 on the representation. And I'll write G hat S for all those representations where the simple reflection acts by -1. So we know everything about how S acts on these representations where S is in the tau invariant. What if S isn't in the tau invariant? So there's a sort of dichotomy. So this one I'm attributing to Borho, Janssen, Duflo, and Zuckerman. It says, if you have an irreducible representation and a simple reflection in the integral Weyl group, then there are two things that can happen. One is that the simple reflection acts by -1. And the alternative is you get this amazingly, well, it's fairly simple formula that when you act by S, you get the representation you started with together with some non-negative integer combination of representations pi prime where S acts by -1. So if I list all of the irreducible representations by putting the ones with S in the tau invariant last, then the matrix for this simple reflection takes this form. If I act, so the first columns of the matrix have to do with acting on a representation where S is not in the tau invariant. So with these formulas, and always what happens is I get what I started with plus some error term that's made out of the second kind of representation. And of course, on the second kind of representation, I'm always acting by -1. So this is the shape. And it's I don't know, it's taken me decades, and I still don't really believe that any matrix of this shape, I0, M minus I, has order 2. But it does. David doesn't believe it either. Anyway, that's true. Okay, so this is getting a little bit interesting. So what comes next? So I'm not going to tell you how to prove that theorem, but I'll say a couple of words about it. So geometric representation theory begins on what's called the complete flag variety for G, the smooth projective variety of all the Borel subgroups of this complex reductive group. So one of the main facts about that smooth projective variety is that the cohomology, I mean, even the cohomology with Z coefficients is torsion free, and the rank is the order of the Weyl group. This B is a kind of geometrization of W. A little more precisely, what happens, the way you go from W to B is that each element of the Weyl group goes to a cell of dimension the length of W. So what happens is that you take all these affine spaces, one for each Weyl group element, space of dimension the length of the Weyl group element, and you can glue them together to make a smooth projective variety. It's stunning. So this Weyl group is generated, of course, by this set of simple reflections. What goes on in the geometry for that is, for each simple reflection, you can talk about, instead of Borel subgroups, you can talk about minimal parabolic subgroups of type S. And so that's, each Borel subgroup is contained in a unique minimal parabolic of type S. So you get a
maximal.
no, I mean minimal proper, minimal not solvable. This is a P1 bundle and not something with bigger. And well, you learn in algebraic geometry that P1 is something that you can control, behaves in a very nice way. And what happens is that this flag variety is kind of an iterated P1 bundle. That's I mean, very roughly, what's going on is that this flag variety looks like a product of this many copies of P1.
That can be true, right?
Sorry? No, of course it's absolutely
For the
not true.
homology.
It's absolutely not true. But it's and it actually it isn't even close enough. I should say this is close to being an iterated P1 bundle. And this is the number of iterations. It is the length of the longest element of W. That's a little. Anyway. So. What geometric representation theory tells you is that the representation theory of G should sort of fiber over the representation theory of SL2 for every simple root S. And the theorem on the previous slide, this dichotomy is a version of that. If you think about what happens for SL2, it's a very simplified version of this. And the theorem says you get it for any G. Okay, so that's roughly. So I was interested in cells. So I have this Borho-Janssen-Duflo dichotomy that a simple reflection acts by either -1 or +1 with a -1 error. One consequence of that is that if the tau invariant of pi is all the simple reflections, then every time I act on pi by a reflection, I get minus pi. I'm never going to get any additional representations. So the cell and the cone are both just pi. And the Weyl group representation that lives there is the sign character of W gamma. The opposite extreme, if the tau invariant is empty, then whenever I act on pi, I'm going to pick up some error terms which have something in their tau invariant. So this cone will be pi and then some terms where the tau invariant is not empty. And it's very easy to see that if you start with this thing where the tau invariant is not empty, you can't get back to pi. So this is what I called, I forget what I called it, sub of pi or something. Anyway, this is what you want to divide by. And after you divide by that, the quotient is just the trivial. The cell is, again, just pi itself, and the Weyl group representation is the trivial representation of W. So in this case, pi is called generic. So things are interesting and difficult when the tau invariant is something in between the empty set and all the simple reflections. So I'm not gonna, and yeah, this was the U21 example that I mentioned. Okay, so
That example is A generic.
sorry.
That example, so A was generic and F was like the sign one.
Yes, that's exactly right. The in this setting, this is the only generic representation, and the last bullet on the previous slide that I skipped was that generic is almost exactly what generic means for automorphic forms. So this is the discrete series which has a Whittaker model. Okay. So suppose now that I've got two simple reflections in the integral Weyl group and that they generate an A2. So it means the product of those reflections has order 3. So I want to single out two special sets of representations. The ones where S is not in the tau invariant, but T is, and the ones where S is in the tau invariant and T is not. Okay? So what I know from this Borho-Janssen-Duflo dichotomy is that if I take something, one of these things where S is not in the tau invariant, and I apply S, I'll get the representation I started with, and then there'll be some error terms which have S in the tau invariant. So some of the error terms will be these B's, some of these B's, and then other error terms will have both S and T in the tau invariant. Same thing when I apply T to one of these B's, I get that B and some of the A's, and then these terms with Z. So if I divide by the Z's, what I find is that the matrix of S has this shape that's maybe getting familiar, that you've got an I in the upper left corner, a minus I in the lower right corner, and then this non-negative integer matrix M. And for T, the opposite. It's just exactly reversed conditions. So what do I know? Well, what we learn from Coxeter is that the most important thing about S and T is this relation that ST cubed is 1. And that relation ST cubed is 1 is the same thing. I'll actually write it over here. I'll write it here. Now this relation ST cubed is equal to 1. It is the same thing as STS is TST. So I've got these two matrices, sigma of S and sigma of T, And I know that I'm getting a representation of S3. And that means that if I multiply S times T times S and T times S times T, I have to get the same thing. So I made this calculation 30 or 40 times, and this was the answer in a clear majority of cases. You would, I mean, any unbiased observer would conclude that I must have screwed up the sign because these two things are the same thing with different signs. But no, as I say, in the clear majority of cases, these signs are correct. And so this relation, which is written here, says that this quantity minus I plus nm has to be 0. So I put that on the next page. And yeah, this condition says that these matrices have to satisfy m times n is the identity and n times m is the identity. By the way, m and n don't have to be square. If you look back, the sizes of n and m are given by the number of these plus minus representations and the number of the minus plus representations. That's two different numbers. And this I is square of size, I don't know, maybe the first order of the first one. And this other I is the identity of the other thing. But it's okay. In these relations, from the red equality, I get that n times m is the identity, and from the blue thing, I get that m times n is the identity. So, in fact, they have to be square. And so now I have m and n are square integer matrices with non-negative entries, which are each other's inverses. It's an easy linear algebra exercise that the only way to get that is with permutation matrices. So the conclusion is that m and n have to be permutation matrices. If you think about what that means in terms of the action of the simple reflections, it says for every one of these simple reflections, there's a unique one of the B's that appears in S applied to A, and, well, the same thing the other way around. For every A, there's a unique, for every B, there's a unique A appearing in T times B. So what do we got? We can now describe completely the cells in type A2. And here's the answer. There are three possible cells. You can have a singleton where the action is trivial. You can have a singleton where the action is the sign. Or you can have a pair of irreducibles, A and B, and the action is given by these 2x2 matrices in the basis AB. So we've completely described what cells can look like in type A2. So I'm out of time. What the idea of this talk was to do the same thing in type BC2. So to take two simple reflections whose product no longer has order 3, but order 4. And it's exactly the same deal. You start out with this matrices that they look the same as before, but now we have this more complicated relation. You have to multiply 4 of these things together. and it's hell, boy. But it's not impossible by any means. And you can get a list of 10 possible ways you can make non-negative integer matrices do these things. You can make M and N. That's the big issue, M and N. And one of the candidates looks like this. Here's two 3x3 matrices. And I claim that if you take the product of these two matrices, that it has order 4. You could try to make a 2x2 example. And if you try to make a 2x2 example, it turns out that you need the product of this number and this number to be 2. And in a symmetric world, you'd want both of those numbers to be the square root of 2. But there's a theorem that the square root of 2 is not an integer. I don't remember the proof precisely, but it's true. And so.
Who are you crediting it to?
This is a theorem of Schmidt. Yeah. So you're forced into having this 2 and the 1 looking not symmetric. And what I was going to do in this talk was explain why you couldn't have this in a cell of representations. And the answer is that those multiplicities are dimensions of X groups. And in this category of irreducible representations of G, the X groups in the two orders are the same. Those numbers that were 1 and 2, one of them is x1 of A and B, and the other one is also x1 of A and B. So we got a problem. So this example is not allowed. Here, these two 1s are dimensions of x1, and these two 1s are the dimensions of x1s. It works. It's all fine. But the 2s don't work. So the point is, for rather elementary reasons, when you want to make a cell, you're forced to use more than 2 representations. So I'll just write the theorem. Yeah, there are 4 possible cells in this BC2 case, and they look like this. The interesting cells have to have 3 representations, and they're exactly the same with the roles of S and T reversed. So you can't have the reflection representation of the Weyl group by itself. It's required that it should come along with a friend in order to get this equality of these numbers and these numbers. So anyway, this is a complete description of what's going on in BC2, and what happens, what was aiming at was that you could use such ideas to say what cells were allowed to look like in general Weyl groups, find a characterization of them using some appropriate integrality, positivity, and symmetry properties. But I squeezed too much and I still took too much time, but thank you very much for your attention, for your cookies, and for the dinner yet to come.
Questions?
You mentioned a cell decomposition of the flag variety with one
Yes.
cell for each Weyl group element.
Yes,
Is that related to the Bruhat decomposition?
it's absolutely the same. Yes, that's well. I mean, yeah, I think that's a fair statement. It's absolutely the same.
Where are the special representations?
So there are these things. Lusztig divided everything into families, and he said whenever you had a cell representation, there had to be a single special representation in it. So what I proved for BC2 was that if you made a cell representation, either it was the trivial representation or it was the sign, or it had to have the reflection representation in it with something else. So that was proving that for BC2, the special representations are trivial and sign and the reflection, and the other two one-dimensional representations are not special.
Maybe just a follow up to that question. So there's an abstract list of special representations, and the goal is to maybe get a concrete list.
Well, so Lusztig has a completely, the list of Weyl group representations was known for classical groups 150 years ago, and for the exceptional groups was worked out in the 1950s. And Lusztig said, these, and these are exactly the special ones. It's all known. The goal is to find a simpler explanation of the answer, to say, okay, what you need is for these representations to live in this kind of nice integral model.
Very good.